volcanic lake that holds 1,000 legends and mysteries. A land for diverse cultural conformity where civilizations live in harmony. A place of dignified tolerance where the seeds of hope are planted, grown, and reaped for prosperity. The genuine miniature of Indonesia.
By declaring the tagline transformation towards the ultimate, Universitas Sumatera Utara is ready to transform into an international standards university with excellent local characteristics. I am Murianto Amin, presenting you Universitas Sumatera Utara.
Starting from Universitas Sumatera Utara Foundation, which collected moral and material support from the people of North Sumatra and Aceh. On August 20th, 1952, the Faculty of Medicine was successfully established. USU was inaugurated as the 7th state university in Indonesia by the first president of the Republic of Indonesia, Sukarno, on November 20th, 1957. Located in Medan City, North Sumatra, USU consists of 2 campuses located in Jalan Dr. Mansur and Kuala Bekala. USU has 15 faculties, 1 graduate school with 163 study programs, and 1 experimental garden covering an area of 300 hectares located in the Tambunan area, Langkat Regency. USU has the vision of becoming a university that has academic excellence as a barometer of scientific advancement that can contend in the global world. Carrying a new spirit, transformation towards the ultimate supports the entire USU academic community to make significant changes to their mindset and work culture per the demands of bureaucratic reform and technological acceleration. Transformation towards the ultimate is indicated by a series of transformations in various sectors. The transformation is realized through collaboration and synergy between the academic community and various parties to create excellent higher education services implemented through Tri Dharma. Campus digitization is an absolute must to provide the best service. Various digital services are provided by USU, such as ASA, e-office, e-agenda, PPID, and also telemedicine. Telemedicine provides easy access for medical treatment to the public through their gadgets. USU has received an A accreditation and is included in Cluster 1 of the Indonesian Ministry of Education and Culture 2020 rankings and ranked 15th university in Indonesia by the Times Higher Education Impact Rankings. USU has also established itself as a part of the international education community. USU is ranked first nationally and ranked 305th in the world in the field of agriculture and biological science at the university level by the Skimago Institutions rankings. In addition, USU is ranked 1201 plus in the world with QS Stars 3 on the Kwak-Farrelly-Simmons World University Rankings 2022 rating agency. As a commercial university, USU is committed to encouraging research to create an USU enterprise by establishing the Institute of Innovation and Business Technology Incubation, or LINKS. LINKS is a place for innovation and research products of USU's academic community to make contributions to society. Some of these innovative products are being prepared for mass production by cooperating with the industrial world and other universities as the implementation of the Merdeka Belajar Campus Merdeka program. Merdeka Belajar Campus Merdeka program is a manifestation of learning by combining theoretical and practical aspects to create excellent human resources. USU collaborates with various partners, from the state-owned company to the government sector, with the aim of creating graduates who are ready and able to follow the needs of the industry and the market. To support comprehensive learning, USU provides integrated facilities. Various facilities available include USU Hospital, Dental and Oral Hospital, Integrated Laboratory, Student Workshop, Auditorium, Student Center, Pancreatic Building, International Guest House, Cafeteria, Student Dormitory, Garden, and various sports facilities.
The spirit of transformation towards the ultimate within the scope of the Tridharma is a manifestation of USU's commitment to produce excellent human resources for the advance of Indonesia.
USU believes that the contribution of all parties is the main key in the effort to transform to be superior. USU, the pride of North Sumatra for Indonesia, transforming to be the best in the world. North Sumatra, a sign of God's love given with full affection, a piece of heaven attached to the earth, home of the world's largest ancient volcanic lake that holds 1,000 legends and mysteries, a land for diverse cultural conformity where civilizations live in harmony, a place of dignified tolerance where the seeds of hope are planted, grown, and reaped for prosperity, the genuine miniature of Indonesia.
By declaring the tagline transformation towards the ultimate, Universitas Sumatera Utara is ready to transform into an international standards university with excellent local characteristics. I am Murianto Amin, presenting you Universitas Sumatera Utara.
Starting from Universitas Sumatera Utara Foundation, which collected moral and material support from the people of North Sumatra and Aceh. On August 20th, 1952, the Faculty of Medicine was successfully established. USU was inaugurated as the 7th state university in Indonesia by the first president of the Republic of Indonesia, Sukarno, on November 20th, 1957. Located in Medan City, North Sumatra, USU consists of 2 campuses located in Jalan Dr. Mansur and Kuala Bekala. USU has 15 faculties, 1 graduate school with 163 study programs, and 1 experimental garden covering an area of 300 hectares located in the Tambunan area, Langkat Regency. USU has the vision of becoming a university that has academic excellence as a barometer of scientific advancement that can contend in the global world. Carrying a new spirit, transformation towards the ultimate supports the entire USU academic community to make significant changes to their mindset and work culture per the demands of bureaucratic reform and technological acceleration. Transformation towards the ultimate is indicated by a series of transformations in various sectors. The transformation is realized through collaboration and synergy between the academic community and various parties to create excellent high education services implemented through Tridharma. Campus digitization is an absolute must to provide the best service. Various digital services are provided by USU, such as ASA, e-office, e-agenda, PPID, and also telemedicine. Telemedicine provides easy access for medical treatment to the public through their gadgets. USU has received an A accreditation and is included in Cluster 1 of the Indonesian Ministry of Education and Culture 2020 rankings and ranked 15th university in Indonesia by the Times Higher Education Impact Rankings. USU has also established itself as a part of the international education community. USU is ranked first nationally and ranked 305th in the world in the field of agriculture and biological science at the university level by the Skimago Institutions rankings. In addition, USU is ranked 1201 plus in the world, with QS Stars 3 on the Kwak-Farrelly-Simmons World University Rankings 2022 rating agency. As a commercial university, USU is committed to encouraging research to create an USU enterprise by establishing the Institute of Innovation and Business Technology Incubation, or LINCS. LINCS is a place for innovation and research products of USU's academic community to make contributions to society. Some of these innovative products are being prepared for mass production by cooperating with the industrial world and other universities as the implementation of the Merdeka Belajar Campus Merdeka program. Merdeka Belajar Campus Merdeka program is a manifestation of learning by combining theoretical and practical aspects to create excellent human resources. USU collaborates with various partners, from the state-owned company to the government sector, with the aim of creating graduates who are ready and able to follow the needs of the industry and the market. To support comprehensive learning, USU provides integrated facilities. Various facilities available include USU Hospital, Dental and Oral Hospital, Integrated Laboratory, Student Workshop, Auditorium, Student Center, Pancasila Building, International Guest House, Cafeteria, Student Dormitory, Garden, and various sports facilities.
The spirit of transformation towards the ultimate within the scope of the Tridharma is a manifestation of USU's commitment to produce excellent human resources for the advance of Indonesia.
USU believes that the contribution of all parties is the main key in the effort to transform to be superior. USU, the pride of North Sumatra for Indonesia, transforming to be the best in the world. North Sumatra, a sign of God's love given with full affection, a piece of heaven attached to the earth, home of the world's largest ancient volcanic lake that holds 1,000 legends and mysteries, a land for diverse cultural conformity where civilizations live in harmony, a place of dignified tolerance where the seeds of hope are planted, grown, and reaped for prosperity, the genuine miniature of Indonesia.
By declaring the tagline transformation towards the ultimate, Universitas Sumatera Utara is ready to transform into an international standards university with excellent local characteristics. I am Murianto Amin, presenting you Universitas Sumatera Utara.
Starting from Universitas Sumatera Utara Foundation, which collected moral and material support from the people of North Sumatra and Aceh, on August 20th, 1952, the Faculty of Medicine was successfully established. USU was inaugurated as the 7th state university in Indonesia by the first president of the Republic of Indonesia, Sukarno, on November 20th, 1957. Located in Medan City, North Sumatra, USU consists of 2 campuses located in Jalan Dr. Mansur and Kuala Bekala. USU has 15 faculties, 1 graduate school with 163 study programs, and 1 experimental garden covering an area of 300 hectares located in the Tambunan area, Langkat Regency. USU has the vision of becoming a university that has academic excellence as a barometer of scientific advancement that can contend in the global world. Carrying a new spirit, transformation towards the ultimate supports the entire USU academic community to make significant changes to their mindset and work culture per the demands of bureaucratic reform and technological acceleration. Transformation towards the ultimate is indicated by a series of transformations in various sectors. The transformation is realized through collaboration and synergy between the academic community and various parties to create excellent higher education services implemented through Tri Dharma. Campus digitization is an absolute must to provide the best service. Various digital services are provided by USU, such as ASA, e-office, e-agenda, PPID, and also telemedicine. Telemedicine provides easy access for medical treatment to the public through their gadgets. USU has received an A accreditation and is included in Cluster 1 of the Indonesian Ministry of Education and Culture 2020 rankings and ranked 15th university in Indonesia by the Times Higher Education Impact Rankings. USU has also established itself as a part of the international education community. USU is ranked first nationally and ranked 305th in the world in the field of agriculture and biological science at the university level by the Skimago Institutions rankings. In addition, USU is ranked 1201 plus in the world with QS Stars 3 on the Kwakwareli-Simmons World University Rankings 2022 rating agency. As a commercial university, USU is committed to encouraging research to create an USU enterprise by establishing the Institute of Innovation and Business Technology Incubation, or LINCS. LINCS is a place for innovation and research products of USU's academic community to make contributions to society. Some of these innovative products are being prepared for mass production by cooperating with the industrial world and other universities as the implementation of the Merdeka Belajar Campus Merdeka program. Merdeka Belajar Campus Merdeka program is a manifestation of learning by combining theoretical and practical aspects to create excellent human resources. USU collaborates with various partners, from the state-owned company to the government sector, with the aim of creating graduates who are ready and able to follow the needs of the industry and the market. To support comprehensive learning, USU provides integrated facilities. Various facilities available include USU Hospital, Dental and Oral Hospital, Integrated Laboratory, Student Workshop, Auditorium, Student Center, Pancasila Building, International Guest House, Cafeteria, Student Dormitory, Garden, and various sports facilities.
The spirit of transformation towards the ultimate within the scope of the Tri Dharma is a manifestation of USU's commitment to produce excellent human resources for the advance of Indonesia.
USU believes that the contribution of all parties is the main key in the effort to transform to be superior. USU, the pride of North Sumatra for Indonesia, transforming to be the best in the world. North Sumatra, a sign of God's love given with full affection, a piece of heaven attached to the earth, home of the world's largest ancient volcanic lake that holds 1,000 legends and mysteries, a land for diverse cultural conformity where civilizations live in harmony, a place of dignified tolerance where the seeds of hope are planted, grown, and reaped for prosperity. The genuine miniature of Indonesia.
By declaring the tagline transformation towards the ultimate, Universitas Sumatera Utara is ready to transform into an international standards university with excellent local characteristics. I am Murianto Amin, presenting you Universitas Sumatera Utara.
Starting from Universitas Sumatera Utara Foundation, which collected moral and material support from the people of North Sumatra and Aceh. On August 20th, 1952, the Faculty of Medicine was successfully established. USU was inaugurated as the 7th state university in Indonesia by the first president of the Republic of Indonesia, Sukarno, on November 20th, 1957. Located in Medan City, North Sumatra, USU consists of 2 campuses located in Jalan Dr. Mansur and Kuala Bekala. USU has 15 faculties, 1 graduate school with 163 study programs, and 1 experimental garden covering an area of 300 hectares located in the Tambunan area, Langkat Regency. USU has the vision of becoming a university that has academic excellence as a barometer of scientific advancement that can contend in the global world. Carrying a new spirit, transformation towards the ultimate supports the entire USU academic community to make significant changes to their mindset and work culture per the demands of bureaucratic reform and technological acceleration. Transformation towards the ultimate is indicated by a series of transformations in various sectors. The transformation is realized through collaboration and synergy between the academic community and various parties to create excellent higher education services implemented through Tri Dharma. Campus digitization is an absolute must to provide the best service. Various digital services are provided by USU, such as ASA, e-office, e-agenda, PPID, and also telemedicine. Telemedicine provides easy access for medical treatment to the public through their gadgets. USU has received an A accreditation and is included in Cluster 1 of the Indonesian Ministry of Education and Culture 2020 rankings and ranked 15th university in Indonesia by the Times Higher Education Impact Rankings. USU has also established itself as a part of the international education community. USU is ranked first nationally and ranked 305th in the world in the field of agriculture and biological science at the university level by the Skimago Institutions rankings. In addition, USU is ranked 1201 plus in the world with QS Stars 3 on the Kwakwareli Simmons World University Rankings 2022 rating agency. As a commercial university, USU is committed to encouraging research to create an USU enterprise by establishing the Institute of Innovation and Business Technology Incubation, or LINKS. LINKS is a place for innovation and research products of USU's academic community to make contributions to society.
Selamat sore, adik-adik mahasiswa. Untuk mahasiswa dari farmasi, boleh live Zoom dulu sebentar. Nanti kalian masuknya via YouTube saja ya. Ini karena nampaknya room Zoom kita tidak mencukupi. Oke, kami beritahukan sekali lagi kepada mahasiswa dari farmasi USU, mungkin bisa live ke YouTube ya, pindahnya ke YouTube. Link YouTube sudah saya bagikan ke grup kelasnya masing-masing. Oke, terima kasih. Assalamualaikum warahmatullahi wabarakatuh.
lancur sisa melamering ismo bagai turang ale mardida kalakmo bekel masada duan dando ale kaditapo duan dando ale kaditapo.
North Sumatra, a sign of God's love given with full affection, a piece of heaven attached to the earth, home of the world's largest ancient volcanic lake that holds 1,000 legends and mysteries, a land for diverse cultural conformity where civilizations live in harmony, a place of dignified tolerance where the seeds of hope are planted, grown, and reaped for prosperity. The genuine miniature of Indonesia.
By declaring the tagline transformation towards the ultimate, Universitas Sumatera Utara is ready to transform into an international standards university with excellent local characteristics. I am Murianto Amin, presenting you Universitas Sumatera Utara.
Starting from Universitas Sumatera Utara Foundation, which collected moral and material support from the people of North Sumatra and Aceh, on August 20th, 1952, the Faculty of Medicine was successfully established. USU was inaugurated as the 7th state university in Indonesia by the first president of the Republic of Indonesia, Sukarno, on November 20th, 1957. Located in Medan City, North Sumatra, USU consists of 2 campuses located in Jalan Dr. Mansur and Kuala Bekala. USU has 15 faculties, 1 graduate school with 163 study programs, and 1 experimental garden covering an area of 300 hectares located in the Tambunan area, Langkat Regency. USU has the vision of becoming a university that has academic excellence as a barometer of scientific advancement that can contend in the global world. Carrying a new spirit, transformation towards the ultimate supports the entire USU academic community to make significant changes to their mindset and work culture per the demands of bureaucratic reform and technological acceleration. Transformation towards the ultimate is indicated by a series of transformations in various sectors. The transformation is realized through collaboration and synergy between the academic community and various parties to create excellent higher education services implemented through Tri Dharma. Campus digitization is an absolute must to provide the best service. Various digital services are provided by USU, such as ASA, e-office, e-agenda, PPID, and also telemedicine. Telemedicine provides easy access for medical treatment to the public through their gadgets. USU has received an A accreditation and is included in Cluster 1 of the Indonesian Ministry of Education and Culture 2020 rankings and ranked 15th university in Indonesia by the Times Higher Education Impact Rankings. USU has also established itself as a part of the international education community. USU is ranked first nationally and ranked 305th in the world in the field of agriculture and biological science at the university level by the Skimago Institutions rankings. In addition, USU is ranked 1201 plus in the world with QS Stars 3 on the Kwakwareli Simmons World University Rankings 2022 rating agency. As a commercial university, USU is committed to encouraging research to create an USU enterprise by establishing the Institute of Innovation and Business Technology Incubation, or LINKS. Links is a place for innovation and research products of USU's academic community to make contributions to society. Some of these innovative products are being prepared for mass production by cooperating with the industrial world and other universities as the implementation of the Merdeka Belajar Campus Merdeka program. Merdeka Belajar Campus Merdeka program is a manifestation of learning by combining theoretical and practical aspects to create excellent human resources. USU collaborates with various partners, from the state-owned company to the government sector, with the aim of creating graduates who are ready and able to follow the needs of the industry and the market. To support comprehensive learning, USU provides integrated facilities. Various facilities available include USU Hospital, Dental and Oral Hospital, Integrated Laboratory, Student Workshop, Auditorium, Student Center, Pancasila Building, International Guest House, Cafeteria, Student Dormitory, Garden, and various sports facilities.
The spirit of transformation towards the ultimate within the scope of the Tridharma is a manifestation of USU's commitment to produce excellent human resources for the advance of Indonesia.
USU believes that the contribution of all parties is the main key in the effort to transform to be superior. USU, the pride of North Sumatra for Indonesia, transforming to be the best in the world. North Sumatra, a sign of God's love given with full affection, a piece of heaven attached to the earth, home of the world's largest ancient volcanic lake, that holds 1,000 legends and mysteries. A land for diverse cultural conformity where civilizations live in harmony. A place of dignified tolerance where the seeds of hope are planted, grown, and reaped for prosperity. The genuine miniature of Indonesia.
By declaring the tagline transformation towards the ultimate, Universitas Sumatera Utara is ready to transform into an international standards university with excellent local characteristics. I am Murianto Amin, presenting you Universitas Sumatera Utara.
Starting from Universitas Sumatera Utara Foundation, which collected moral and material support from the people of North Sumatra and Aceh. On August 20th, 1952, the Faculty of Medicine was successfully established. USU was inaugurated as the 7th state university in Indonesia by the first president of the Republic of Indonesia, Sukarno, on November 20th, 1957. Located in Medan City, North Sumatra, USU consists of 2 campuses located in Jalan Dr. Mansur and Kuala Bekala. USU has 15 faculties, 1 graduate school with 163 study programs, and 1 experimental garden covering an area of 300 hectares located in the Tambunan area, Langkat Regency. USU has the vision of becoming a university that has academic excellence as a barometer of scientific advancement that can contend in the global world. Carrying a new spirit, transformation towards the ultimate supports the entire USU academic community to make significant changes to their mindset and work culture per the demands of bureaucratic reform and technological acceleration. Transformation towards the ultimate is indicated by a series of transformations in various sectors. The transformation is realized through collaboration and synergy between the academic community and various parties to create excellent higher education services implemented through Tri Dharma. Campus digitization is an absolute must to provide the best service. Various digital services are provided by USU, such as ASA, e-office, e-agenda, PPID, and also telemedicine. Telemedicine provides easy access for medical treatment to the public through their gadgets. USU has received an A accreditation and is included in Cluster 1 of the Indonesian Ministry of Education and Culture 2020 rankings and ranked 15th university in Indonesia by the Times Higher Education Impact Rankings. USU has also established itself as a part of the international education community. USU is ranked first nationally and ranked 305th in the world in the field of agriculture and biological science at the university level by the Skimago Institutions rankings. In addition, USU is ranked 1201 plus in the world with QS Stars 3 on the Kwakwareli Simmons World University Rankings 2022 rating agency. As a commercial university, USU is committed to encouraging research to create an USU enterprise by establishing the Institute of Innovation and Business Technology Incubation, or LINCS. LINCS is a place for innovation and research products of USU's academic community to make contributions to society. Some of these innovative products are being prepared for mass production by cooperating with the industrial world and other universities as the implementation of the Merdeka Belajar Campus Merdeka program. Merdeka Belajar Campus Merdeka program is a manifestation of learning by combining theoretical and practical aspects to create excellent human resources. USU collaborates with various partners, from the state-owned company to the government sector, with the aim of creating graduates who are ready and able to follow the needs of the industry and the market. Of learning, USU provides integrated facilities. Various facilities available include USU Hospital, Dental and Oral Hospital, integrated laboratory, student workshop, auditorium, student center, Pancasila building, international guest house, cafeteria, student dormitory, garden, and various sports facilities.
The spirit of transformation towards the ultimate within the scope of the Tridharma is a manifestation of USU's commitment to produce excellent human resources for the advance of Indonesia.
USU believes that the contribution of all parties is the main key in the effort to transform to be superior. USU, the pride of North Sumatra for Indonesia, transforming to be the best in the world.
Dear participants, we will start this event, so please be prepared.
North Sumatra.
Make sure that you have a good internet connection to enjoy this event perfectly. Thank you. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon from Indonesia and welcome to today's webinar. This webinar is part of World Class University program of Universitas Sumatera Utara. I am Dr. Emil Salim from the Faculty of Pharmacy, Universitas Sumatera Utara, as your Master of Ceremony. First of all, let's thank God, Allah Subhanahu wa Ta'ala, for His grace and guidance so we can join this webinar. The Honorable Rector of Universitas Sumatera Utara, Dr. Murianto Amin, Vice Rector 3 of Universitas Sumatera Utara, Professor Poppy Angelisa Zaitun Hasibuan, Dean of Faculty of Pharmacy of Universitas Sumatera Utara, Dr. Khairun Nisa, World Class University Team of Universitas Sumatera Utara, Speaker Professor Khulaud Al-Jamal, Host Mrs. Dwi Lestari, Master of Science, participants from Indonesia, Malaysia, Pakistan, the UK, and other countries. First, I would like to invite the Rector of Universitas Sumatera Utara to give a welcome speech and open this event. Please welcome Dr. Murianto Amin.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Salam, Om Swastiastu, Namo Buddhaya, salam kebajikan, selamat sore, good afternoon, dan salam sehat bagi kita semua. Yang saya hormati, Profesor Khulaud Al-Jamal from King's College London, United Kingdom, as a speaker, para wakil rektor Universitas Sumatera Utara, staf ahli rektor, para dekan dan wakil dekan di lingkungan Universitas Sumatera Utara, dan yang kami hormati Ketua Tim Class University yang hadir, moderator Ibu Dwi Lestari SSC MSc APT, Bapak Ibu para dosen peserta webinar. I must to talk with the bahasa because many participants is from Indonesia. I am sorry for Professor Khulaud Al-Jamal because I speak in bahasa. Pertama sekali, marilah kita mengucapkan puji dan syukur kehadirat Allah Subhanahu wa Ta'ala, Tuhan Yang Maha Esa. Pada kesempatan yang berbahagia ini kita masih bisa menghadiri kegiatan webinar Top Scientist is the one of part activities from the World Class University programs by the Universitas Sumatera Utara. Ibu Bapak hadirin yang saya hormati, pertama sekali kami mengucapkan thank you and welcome for Professor Khulaud Al-Jamal from the Department Institute of Pharmaceutical Science, King's College London, United Kingdom, as speakers in these seminars, virtual seminars. Professor Kolut will talk about the exosomes in pancreatic cancer, from early detection to therapeutics delivery. I think these topics needed by Universitas Sumatera Utara as students, both students and lecturer, to develop one of the pusat unggulan ilmiah in our university in the field of tropical medicines. Dalam pertemuan dan kesempatan yang berbahagia ini juga, kita berharap Profesor Khulud Al-Jamal bisa memberikan sharing informasi dan pengalamannya kepada kita semua, khususnya untuk dosen dan mahasiswa yang mempelajari mengenai topik-topik kanker dan perobatannya serta turunan-turunannya. Yang kita tahu bahwa secara simultan itu juga akan bisa meningkatkan kualitas dan kuantitas pelayanan medis, riset, dan juga publikasi yang dilakukan di masa-masa mendatang. Saya juga berharap agar Profesor Khulud Al-Jamal bisa kita undang sebagai foreign lecture to give some experience to our students and our lecture, especially to upgrade or to make some many perspective, competence and skills of the scientists, so that kita berharap Profesor Khulud bisa mengajar sebagai dosen asing di Universitas Sumatera Utara, khususnya di program studi yang ada di farmasi, dan bisa melakukan research collaboration dengan dosen dan mahasiswa terhadap topik-topik tertentu. Kita menyediakan berbagai fasilitas yang dibutuhkan untuk itu, dan kami berharap Ibu Dekan dan dengan dosen yang bisa memberikan semacam insight bagi dosen kita ini, bagi Profesor Khulud Al-Jamal, untuk meyakinkan bahwa kita akan menyediakan beberapa skema riset yang nanti bisa dibantu oleh Profesor Khulud sampai dengan terbitnya misalnya publikasi bersama dari riset-riset bersama yang dilakukan dalam kurun waktu tertentu. Ini kita lakukan agar semua kegiatan-kegiatan yang berkaitan dengan general lecture yang diberikan oleh dosen-dosen asing itu bisa mendukung kita untuk masuk ke level standarisasi internasional. Bukan hanya untuk kepentingan World University Ranking, tetapi yang lebih penting adalah kita meningkatkan pengetahuan kita tentang tema-tema riset, dan hasilnya itu bisa bermanfaat bagi dunia akademik dan juga bisa memberikan solusi bagi permasalahan-permasalahan yang ada di masyarakat. Ibu Bapak yang saya hormati, riset dan penulisan ilmiah menjadi hal yang sangat penting sekarang di dunia akademik. Semua dosen diharapkan bisa memiliki satu riset, satu publikasi dalam bidangnya, dan juga bisa berkaitan dengan bidang-bidang kompetensi bidang ilmu yang lain, selama misalnya itu bisa mendukung kinerja, reputasi, dan daya saing yang dimiliki oleh dosen, begitu juga mahasiswa. Sampai hari ini misalnya minat para dosen dan mahasiswa di Universitas Sumatera Utara dalam melakukan riset itu masih belum begitu merata. Karena itu kita perlu memberikan atau melakukan berbagai macam effort untuk bisa memotivasi bagi para dosen untuk mengajak para mahasiswanya agar kita bisa meningkatkan kualitas atau kompetensi kita di bidang riset dan penulisan publikasi ilmiah. Karena itu, general lecture yang kita lakukan hari ini dalam rangka World Class University itu bisa selain memberikan pemikiran baru, juga memotivasi kita untuk mengusulkan satu proyek riset yang dibiayai oleh universitas, juga bisa mencari sumber-sumber dana hibah dan kompetisi riset ilmiah seperti di kementerian melalui skema DRPM, lalu juga bisa skema riset yang diberikan oleh Badan Riset Inovasi Nasional atau BRIN, atau juga riset-riset yang dibiayai oleh lembaga-lembaga swasta atau juga lembaga-lembaga kementerian yang lainnya yang kemudian bisa memberikan dampak bagi program kerja yang mereka perlukan untuk membuat sebuah kebijakan teknis yang kemudian bisa mengurangi berbagai masalah yang ada di masyarakat. Itulah tujuannya kita melakukan yang namanya general lecture dalam World Class University ini. Sehingga para peneliti, para dosen yang kita undang sebagai narasumber itu bisa kita lakukan kolaborasi tindak lanjut. Jadi bukan berhenti hanya sebagai posisinya sebagai general lecture atau sebagai narasumber pada satu kegiatan saja. Kelanjutannya bahwa narasumber yang kita undang ini bisa memberikan berbagai macam kegiatan lainnya secara kolaboratif dengan dosen, program studi, dan kemudian memberikan sumbangan terhadap luaran dari riset yang kita lakukan bersama-sama. Inilah harapan kami semua agar kegiatan World Class University Top Scientist yang kita selenggarakan hari ini bisa memberikan banyak manfaat bagi kehidupan manusia secara umum, tapi secara khususnya untuk meningkatkan kompetensi dosen dan mahasiswa dalam rangka melakukan riset dan menulis publikasi serta menemukan sebuah inovasi untuk penyelesaian masalah-masalah kemasyarakatan yang berhubungan dengan disiplin ilmu masing-masing dari kita sendiri. Ibu Bapak hadirin yang saya hormati, again we would like to thank you for Professor Khulud Al-Jamal because want to take this momentum to give some experience, some best experience, and some information about the cancer, about the and other relevant discipline for our lecture and our student. Dengan mengucapkan Bismillahirrahmanirrahim, saya membuka webinar Top Scientist World Class University Program. Selamat mengikuti, semoga Allah Subhanahu wa taala Tuhan yang Maha Esa senantiasa memberikan jalan terbaik dan meridhoi seluruh upaya kita. Terima kasih. Billahi taufik wal hidayah. Assalamualaikum warahmatullahi wabarakatuh. Salam Santi 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 Namo Buddhaya.
Thank you very much, Chairman. I don't know, can I start or Emil? Can you hear me?
Oh, okay, yes, I hear you.
Let me know when I should start. Yeah, I'll wait.
Okay, thank you very much. Okay, now I will give to Mrs. Dwi to guide this webinar. Please, Mrs. Dwi and Professor Khulud, time is yours.
Okay, thank you, Mr. Emil Salim, and also Mr. Rector, Pak Mulyanto Amin, for the introduction. And thank you for all the participants to join in our webinar in this afternoon. First of all, good morning, Professor Khulud. I think it is morning still there in London. How are you?
I'm very well, thank you very much.
Yes, welcome in our webinar sitting in here we are in Medan now. It's about at 4 in the afternoon. So yeah, so we are so blessed that we can join today in this Friday during this pandemic situation. But yeah, with this virtual Zoom that it's allowing us to meet here. So yeah, we cannot wait for your interesting presentation. And yeah, thank you for accepting our invitation to share your expertise in nanomedicine. And thank you also, I want to thank to Stefan, our former student, that also your students in King's College. Yeah. Before we proceed to hearing Professor Kolot's presentation, let me introduce our distinctive speaker this afternoon. So Professor Kolot got her BSc in pharmacy from University of Petra Jordan, and then she got her MPhil philosophy and PhD from the School of Pharmacy that known as University College London from UK. And since then, she had been working all around the world, also in as visiting professor in Sapienza University of Rome, Italy, from 2016 till now, and also visiting professor in Guizhou University in Guiyang, China. And at the moment, she becomes a professor in drug delivery and nanomedicine in Institute of Pharmaceutical Science, Department of Pharmacy and Forensic Science, King's College of London, UK, and also becomes a head of medicines development of King's College London, UK. And she got also very interesting awards and fellowships, especially that one that impressive is in 2012, she got the Royal Pharmaceutical Science Award for her achievements in nanomedicines from the Royal Pharmaceutical Society, that's recorded as a third female to obtain it in 43 years history. So yeah, we can wait for hearing from you, Professor. So for not being so long, the time is yours. Please, Mr. Kolot.
So thank you very much. Thank you. I'm really humbled by the welcome and the introduction, and thank you for the invitation. Thank you, Stephen, for mediating this invitation. Stephen was my master's student last year, and I think he did a good job representing Indonesia. I also have a PhD student at the moment, Rifka Utami. She's also from Indonesia, and she's doing a great job. So I welcome to have more students from Indonesia. So I will share my screen if that's okay. Let's see if it's okay, because this is a new computer. So I'm going to try now. So share screen. Okay. So let's do this. Okay, so this. Do you see the big screen or the small screen? Can someone tell me, do you see the full screen or the small one?
Big screen.
Big screen. Okay, perfect. So small screen now?
Okay, yes, no, big screen.
Now big, okay, perfect. So I won't see any of you. So if you have questions, you may want to, I don't know, stop me or wait till the end. We'll have a final session at the end. Okay, so today I'm going to select one topic of work that we do in the lab, which is our work on exosomes. So I will show you some examples how we can use exosomes or extracellular vesicles to treat pancreatic cancer or to deliver drugs to treat pancreatic cancer, but how we can also use them for early detection of pancreatic cancer. Is the sound clear? Everything is fine? Can you hear me? Everything is okay?
Yes, everything is okay, Professor.
Okay. Right, so I decided to give you some background about King's, some background about myself, since we have some time to discuss today. So at the moment, I am based at the Waterloo campus, which is one of 6 campuses that belong to King's College London. So if you've been to UK, this is the Thames River. And you have some of these touristic places. This is the House of Parliament. This is St. Thomas Hospital. This is the St. Paul Cathedral. So you have a few of the nice attractions around us. And we are based particularly here near the IMAX cinema. So we are scattered across the south of the river, if you want to call it. So you cross the river, except, 2 buildings were mostly south of the river. So among the UK universities, King's has been ranked actually 7th among UK university according to the QS World Ranking. We are 31st across the world. Maybe this number has changed because it was in 2019, but I think we can say that we are one of the top 50 universities worldwide. So we are proud to have a number of Nobel laureate who are from King's. So some of the ones you may recognize, particularly in the pharmacy fields, are with asterisk here. So we have Hopkins, who discovered vitamins. We have Sherrington, who discovered the nervous system, and a few, very proud of the Wilkins, who discovered the structure of DNA, and Black, who discovered beta blockers and anti-ulcer drugs. Very recently, we had Leavitt, who discovered something on protein structure. So from time to time, we get one Nobel laureate from King's. So this is great news. We're also one of the few universities in UK who form affiliation with clinical partners. So we partner with hospitals, four major hospitals: Guy's Hospital, King's College Hospital, St. Thomas Hospital, to form what we call King's Health Partners. So we like scientists to work with clinicians because we feel we would like to translate what we do to the rest of the world for the benefit of patients. We have 8 faculties at King's. So I am particularly part of life science and medicine, which is one of the 8, and it hosts 7 separate schools. We are based at the School of Cancer and Pharmaceutical Science, one of 7 within the life science and medicine. So you can imagine the structure is so big that we have faculties, we have schools, and we have divisions under the schools. So I come from the Institute of Pharmaceutical Science, which is part of the School of Cancer and Pharmaceutical Science in Life Science and Medicine faculty. We have approximately 6,099 undergraduate students. So this is where I come from, IPS, and we are approximately 38 PIs with a number of PhD students, postdocs, and we have a master course program, which Stephen has attended, and we also have undergraduate pharmacy degree. We call it an MPharm degree, and approximately we have 100 to 150 per year students. So IPS has 3 main themes: drug discovery, medicine development, and medicine use. And I am the head of medicine development section within IPS. So I'll tell you a little bit about how my journey started. So back in 2000, I graduated with pharmacy from Jordan. And during my undergrad, I was very passionate about doing research. So I was preparing myself that after I graduate, I would like to work in the university for a year or two, and then take this opportunity to apply for PhD abroad. So I had two directions. I was first interested in doing a drug delivery to the eye in USA. And I also was corresponding with some UK universities. One way or another, it happened that my way to USA was not as smooth as the one to UK. So I landed to London. I started my PhD with Professor Alexander Florence, who was at that time at the School of Pharmacy, University of London, which is now called UCL School of Pharmacy. So you may recognize me, I'm here. And this was back in the 2000 when I was one of a few within the group. It was a lovely group, an international group with a great leader. In 2018, I was the group leader, and I had a lovely group of international students helping me to do all the exciting research that I will present to you today. So the moral of the story, in less than 20 years, you can turn to become a professor. If you are really keen and you want to do it, you can do it. So some of the key dates, I have been kindly introduced in terms of CV, but I would like to tell you some of the milestone dates in my life. So in 1998, I graduated with a bachelor degree, and I was awarded my PhD in 2004, officially registered as 2005 because I took a gap year doing my pre-registration year in the hospital. So I wanted to become trained pharmacist. And that's because I believe it's very important when we educate our pharmacy students, we know what it is like to be a pharmacist and undertake the full registration. I then left the hospital and I came back to academia, and I took a fellowship, a very prestigious fellowship called the Maplethorpe Fellowship. I did 2 years of independent research. I was part of the group. I was doing my own research, but also teaching at the university. So I had a mini exposure to what lecturer life will be like. I then progressed to take a more senior role within the group. So for another 3 years, I was kind of a deputy group leader, helping students and postdocs to do their work. And with that, I gained a lot of experience, especially on the preclinical studies and imaging, which I'm very grateful for. In 2010, I was lost. What do I want to do with my life? And I explored various options, industry, academia, applying for fellowships. And I was lucky in 2011 to have an assistant professor, or in UK, they call it a lecturer, at the Institute of Pharmaceutical Science in Nanomedicine. I progressed very quickly. So in 3 years' time, I was promoted to an associate professor and then a reader. And then in 2016, I became a full professor in drug delivery and nanomedicine. With that, I was the first in UK, they call it BAM, which is Black and Ethnic Minority Group, to become a female professor under the age of 40. So I talked to you about this Maplethorpe Fellowship, and this Maplethorpe Fellowship is a good initiative that some universities and charities implement, which I think is something that also Indonesia can be looked at, because what it does, it picks researchers who have great promise, and it prepares them to undertake their own independent research immediately after their PhD, and also have some exposure to teaching. So they're not teaching heavy, and they are also able to explore their own ideas. So you can see here, this was when I was awarded. My topic was on, during my PhD, I synthesized polylysine dendrimers, and I was exploring them as drug delivery agents. Incidentally, I found I was trying to deliver heparin as a drug, and I found they form complexes or very nice particles with dendrimers, because dendrimer has a positive charge while heparin has a very high negative charge, like in nucleic acids. So they form nice particles. And I was looking at applications because obviously they will not deliver heparin, because heparin will become inactivated when binding heparin. So my initial idea failed and was very disappointed because I could see heparin is no longer active. Reading a little bit more in the literature, I thought I could have another application, which is heparin is highly abundant on blood vessels, and it is important for promoting angiogenesis. So I hypothesize if I deliver these polylysine dendrimers and they reach the tumor, they will basically coat the endothelial layer and they will stop formation of blood vessels. And this was my idea for this fellowship. And we published a PNAS paper from this. So this was a very important step in my career. And this is where I actually got exposed, switched from doing chemistry into preclinical testing. In 2012, soon after I joined King's College London, I was awarded this very prestigious award called the Royal Pharmaceutical Science Award for Nanomedicine. And this is very special to me because if you notice something here, everyone here is a male. In 2006, we have some names who are females. So we've got Molly Stevens, Yvonne Berry. And in 2011, not only I was the third female to get this in a 43-year history, but I was the only foreign female who gets this award. So this was rewarding for me and surprising. I would like to tell you also, in addition to our research, I'm very interested in publishing and books. So me and my team, my students helped me to contribute to a number of books, and particularly this one, which I edited myself on neurobiology. So maybe our numbers changed here a little bit, but we've constantly had a number of teaching and research fellows, postdocs, PhD students, and master and MPharm students. Our research is funded by a number of funding bodies, because without those funders, we are unable to recruit postdocs who are very helpful to train PhD students in addition to me, because I'm this available in the lab. So, we rely on experienced researchers to support the group, and they're key members of the group. So in 2019, a Getty Imager professional photographer visited our lab because she wanted to feature the woman in science. Now, I'm delighted to say, actually, now my group, except 2 of them, they're all females. So we've grown as female scientists, but I'm trying to get the balance back, because it's good. It's always good to have this gender balance in the group. So we welcome more male PhD students at the moment. Okay, so about 55 researchers and postdoctoral fellows came to my lab, either as my postdocs or as visiting researchers from different labs. We're delighted to have this experience because we made good friends with people from everywhere in the world. I'm also delighted we had some couples in the group, either during, like Lizzo and Danny, or after they left. We had some happy moments from these interactions. I told you I'm very interested in sharing our experience and knowledge with public, because it's very important that the public knows what scientists do, because that enhances the provision of some charity funding, donation to universities, and they also understand sometimes, for example, why are we using animals for our own research, and appreciate. For example, now when the vaccine has emerged, a lot of fears, people are fearful of the vaccine. If we educate them how we are making these vaccines, how we ensure there is safety and rigor in making them, I think the gap will become less big. So I'm proud to say I am a 3-time Image Award winner. So the Wellcome Trust here is a big charity funder in UK, and they promote the interaction with the public. So every year they propose people put their science for image winning, and we got this in 3 times in a row. With my student, so Izzat has contributed to all of these, and he's from Malaysia. May, he's from Taiwan. He's now doing a postdoc in the States. I have this image at the moment on the wall. You may not be able to see it. We also open our lab to accept charity supporters. So this was a trip. Here is Farid. I think he's also with us now listening from Malaysia, and the rest of the group. And what we did here, we invited charity supporters. So people you see in this family, either they had brain cancer or one of their family members had brain cancer. So we really invited them and showed them how we try to develop new treatments for brain cancer. And they were delighted. They wrote a blog about what they felt. It was really heartwarming to see what impact it made on them. We contributed to some charity marathons and wrote in public magazines. So I hope the message, what I'm trying to say is we shouldn't be enclosed on ourselves and just do the research that no one knows about. We should try and communicate it to wider than the scientific community. So I'll move a little bit now on drug delivery and what is drug delivery and how exosomes is linked to this. There are many diseases that have treatments, and the science had advanced so much that we pretty much have the treatments for most of the diseases, but there are still some diseases with no treatments, or some treatments that have severe side effects that sometimes require us to interrupt the therapy, like with cancer chemotherapy. Sometimes the patients cannot tolerate the side effects and you have to terminate the treatment. So with drug delivery, we're trying to overcome these problems by either getting the drug to the right site of action. So what it means, maybe the drug is too water soluble, the drug is too lipidic, and we would like to get more of that drug at the site of action. Maybe this is the brain, maybe this is pancreatic cancer. So what we try to do is learn about how the tumor and the brain protect themselves and use this as a weapon. So we design a delivery system that is able to hijack this protection and deliver the drug to the site of action. We do this either to treat the disease or try to diagnose it early, or after treatment, we would like to monitor, is the disease coming back? So nanomedicine will be useful. So drug delivery, simply, you are changing the pharmacokinetic of a drug. So a drug has a pharmacokinetic profile that is not preferred, and I would like to make it better. And when I say better, I want to get more of the drug as the site of action, less of the drug at the off target. So what you do now, for example, you can increase the ratio of the drug at the tumor site and less everywhere. So if I give more of this drug, the patient will not have the side effects, and I am able to kill the tumor because I'm getting more drug in. Drug delivery could happen with nanomedicine or with other modalities. It could happen with physical means. It could happen using biomaterials, microparticles. So if I use nano carriers, if I use nanoscale carriers, that is nanomedicine. So nanomedicine is a type of drug delivery. You can use these drugs. They could be small molecule, they could be large molecule, they could be biologics. It doesn't matter. You are delivering them. You are improving their performance by putting them in a carrier that protects them, and they behave like the carrier. I could go to the station and walk at a certain speed. I could take a car and the car takes me. So when I'm in the car, my behavior is that of the car, and this is exactly what we want to mimic. So nanoparticles are, what makes them nanoparticle? How do I define nanoparticles? It's very important that you visualize there is an interface between those particles and surrounding media. Antibodies are not nanoparticles because they're soluble. They don't have an interface. They don't have their own physical characteristics that makes them colloid. While viruses are nanoparticles because they have their own envelope. So bacteria is too big, they're micron size. So my aim is to make nanoparticles that are sub 100 nanometer size. And why I want them small? Because if they're small, they are able to navigate the cell better. If I have a cell that is 10 micrometer size, the particle is 100 nanometer, they are 1,000 or 10,000 times smaller than these cells. So they can, for example, be targeted to the mitochondria, to the nucleus. Now, if they're too small, you don't want them too small because they will be eliminated very quickly through the kidney. So I need to have them with a size that makes them circulate long, not too big that they are recognized by the macrophages and immune cells, because that means they will be cleared very quickly, and not too small because otherwise they would be excreted from the kidney too fast. So something between 50 and 100 is an ideal size for us. So with targeted drug delivery, you can have a switch of the phenotype. So a free drug could have problems such as the low or very high water solubility. Low water solubility means it cannot be absorbed. High water solubility means it will be excreted very quickly from the body. So we don't want that. We want to have it some sort of intermediate solubility. So I could solubilize highly insoluble drug, or I could put this highly soluble drug in a container that circulate a little bit longer. So I prolong the half-life and bioavailability of these drugs. We could also have non-specific tissue biodistribution if I have a free drug. If I have it in a nanoparticulate form, I could have more control on where they will go into the body. And that could be because of the size of these particles, because of the charge, because of the protein they carry on their surface. So there are various ways of controlling it. You don't have a specific targeting with nanomedicine. You will have specific targeting profile. And because of that indiscrimination in tissue targeting, you have low therapeutic index. The difference between the toxic concentration and therapeutic concentration is narrow. I would like to bring this slightly wider. So the aim of all of this is to really increase the therapeutic index of the drug and improve bioavailability. So when we say bioavailability, if I give 100 milligrams drug orally, and I could only absorb 1% of this drug, 99% of this drug has been excreted. So it's a loss for pharma industry. It's no benefit of the drug. So the more bioavailability I get, the more of that drug gets into the body, the better. But it's quality, not quantity. It's not, I only want to get the drug in, but I want to get it to the right site of action. So we talked about nanocarriers, but what are these nanocarriers? You could have nanocarriers made of polymer. So polymeric nanoparticles. So you have the polymer, because of its low water solubility, you prepare it in a way where it can self-assemble or precipitate and make nanoparticles. You could have it made of lipids like liposomes and exosomes. So lipid material that basically they self-assemble because they don't like to, they are not soluble. So they form some supramolecular structures. They could be made of protein, you could have a carbonaceous material, you could have inorganic material. So the field has advanced so much that you can make them from different material. The drug could vary. You could have small molecule drug, you could have radiations, you could have nucleic acids, protein, and so on. So these examples I mentioned are all carried out in my lab. And we are interested in two main applications at the moment: cancer drug delivery and drug delivery to the brain. We are expanding. So very recently, we will be also working with targeting drugs to the heart. What I like to do when we do these things, I like to image. I like to see the events, whether they are at the cellular level or at the organism level, because that will give us a lot of information how to take this information back and improve your system. Maybe I will find that my system is too toxic or cannot penetrate the target or does not get to the site of action at high concentrations. So I would go back and improve the formulation. And we keep doing this cycle till we come up with a system that is of a good pharmacokinetic profile that then we use to deliver our therapeutics. So the sequence will be, we identify what the unmet clinical need is. What is the problem that we're trying to solve? Then select our drug, select our nanoparticles, and with a careful design, we can develop a system that can solve this particular problem, or we think it can solve this particular problem. We would perform some cell work studies to before going to the animal. Again, to narrow down, maybe I have 100 formulations and I want to be narrowed to 5. So we do that. And then I perform imaging to see, are they of acceptable pharmacokinetic profile? And then we go ahead and do proof of concept therapy. And with that, the preclinical testing is done. And then you would go and talk to the clinicians. Obviously, there will be regulatory issues to solve with regulatory bodies before going into clinical trial. The earlier you engage with these regulatory bodies, the better, because they may tell you, use a polymer that is of known toxicity profile, because you will need to submit this when you apply for a clinical trial. So it's a little bit complex, and it's good to think of all these parameters early in advance, because the aim is do science to translate it. So 20 years in this field, 21, I managed to have exposure to different types of nanoparticles. So all these in blue are actually materials that I worked with. I'm a scientist, so I really like to understand the biophysical interaction and structural activity relationship. So there are processes that we get to know about when applying these delivery systems for particular disease applications. So there's the material knowledge, there is the processes and interactions that you need to be aware of, and then there's the disease that you need to be aware of and what targets you want to pick. And so as you can see, there are a few things to think about. Okay, so now I'm just looking at the time. Yeah, that's fine. Okay, so exosomes. So what are exosomes? If I exclude all these proteins and intracellular targets, and you just see this bilayer, this is a liposome structure. So liposomes are vesicular. Vesicular means you have aqueous core. They are bilayer, so you have 2 layers assembled, and they carry drugs in them. So you could have hydrophobic drugs in the membrane and aqueous drugs in the core. exosomes are different in a way. They carry also their own material. So they come with a signature. They have what the cell contains. They are a mini cell. The cell shed them and they will have proteins, they will have nucleic acids, microRNAs inside them. So they are like a little cell factory on their own. They have emerged. So in 2000 and going back to 2 years now, in 2014, someone came to me and he said to me, what is the difference between exosome and liposomes? And I didn't know what exosomes were. They were new to me. So I looked at them. I gave him some answers, but I said, well, I would like to explore this further. So then Farid, who is with us today, started his PhD. He was finishing his undergrad degree in Cambridge University and came to my lab to do a PhD. And then I said to him, Farid, we would like to use these exosomes to deliver drug to the brain. So Farid was a smart student. He started reading and, do they go to the brain? I mean, this is the first question because there was a paper published that shows that you can have exosomes targeting the brain. Intrigued by imaging, we tried to first see whether they go to the brain, and his PhD ended on finding ways to track these exosomes and image them inside the body. And I think that was very, very useful. Besides, obviously, he started this whole new line of research in my lab from, going, how do we characterize these? We didn't have an NTA in the beginning. So lots of challenges that we managed to overcome in the past year and a half. And I'll show you what was the fruit of these experiments. So exosomes, when I read about them, people were talking about using them as therapeutic targets. So if you identify they could be targeted, you may want to treat a disease. They could be used as therapeutic agents. They carry materials on their own right, and maybe you can deliver them as a drug. In case of the field of regenerative medicine, instead of introducing the mesenchymal stem cells, we would like actually to deliver the exosomes or the byproducts of these cells. We are a drug delivery lab, so I really wanted to see, can I deliver drugs using these exosomes? How can I load them with drugs without altering their properties and so on? So lots of questions. Now we're trying to understand. So there is a student in my lab, Ray. She's from Thailand, and she's trying to understand how these exosomes could be functionalized or what kind of protein corona they carry on their surface, because we can see that there are differences how exosomes distribute into the body if they're from different sizes and on their culturing conditions as well. So, this is, so the first question was, how do I track them? First of all, what exosomes I use, what source of cells, what concentration, what incubation conditions. So there are a lot of factors to design to pick the right carrier. So the literature actually informed us that exosomes can be taken up into cells by different mechanisms, multiple mechanisms. And we wanted to understand a little bit more the effect of size, time, and surface properties on these uptake. We also wanted to understand the effect of the source of these exosomes. So there was another paper published in 2017 that talked about cell tropism. So for example, if you have exosomes produced by SCOV cells, they are taken up better in the cells compared to exosomes that come from a different endogenous type. So if you think about it, if I would like to treat pancreatic cancer, can I take exosomes from pancreatic cancer and feed them with a drug and give them back to the cells, because the cells will be fooled and take them up thinking they are endogenous exosomes. So we read that, but we really wanted to verify it, make sure that I have this tropism characteristic. So this was the work of a postdoc in my lab, Dr. Lizu Zhu, who is now an assistant professor in China. So Lizzo worked with Farid, and he started developing exosomes more targeted to pancreatic cancer based on the data that we generated on the biodistribution profile from Farid's PhD. So we worked with cancer biologists because I like to work with people who know there are targets that have been validated, that targets that are promising, that targets that they need to validate in vivo. So Claire Wells, who is a professor in cancer biology, she works with a family of peptide called the PAC family. So they are a family of proteins that are known to have a key role in proliferation and migration of pancreatic cancer. But there are no data to show, for example, you can silence PAC4 in animal and lead to tumor growth delay. So people use chemical inhibitors. There was an in vivo study showing if you use chemical inhibitors, you are able to delay tumor growth, but nothing was shown using RNAi or gene silencing, so gene therapy, to deliver. And why we want gene therapy? Because gene therapy can be more selective than chemical drug, which could inhibit PAC4 enzyme everywhere. So our hypothesis was, if I can deliver an siRNA in an exosomal carrier, because the exosomal carrier can be taken up efficiently by the cells, then I can knock down PAC4 and I can reduce the proliferation of pancreatic cancer and delay tumor growth. As you know, pancreatic cancer is aggressive to treat for many reasons. One is the discovery of the cancer is normally known quite late because it's asymptomatic. And when they find out, it's very hard to remove it because the way it grows, it spreads into the peritoneal cavity and it sticks on blood vessels. So it's really hard to remove it. So two ways. One is we need to detect it early, but also I need to find efficient carriers. And the third problem with pancreatic cancer is it has a very fibrous nature. So penetration of the drug into the tumor mass is very hard. So if exosomes are able to somehow modulate that fibrous nature of the tumor, because they are meant to know how to overcome the internal barriers, and they are able to enter the cell better, maybe I can solve some of these problems. So the first step is how to decide on our delivery system. So we use something called design of experimental approach. So Stephen has used this also during his master degree. And what advantages we get with this DOE is you can decide on the factors that control the process you're looking into by looking at minimum number of conditions. And you can also look at factor-factor interactions. For example, the effect of size and incubation time. Maybe one of them will work it will affect the uptake in one way, but when they're together, there are two-factor interaction. And what you have at the end is an equation, mathematical equation that gives you a prediction. And with that prediction, I'm able to input some of the information that tells me if you want 90 particles to be taken up by the cancer cells, you need to put 10 to the 9 particles, incubate the cell for 4 minutes, and that gives you the outcome you need. Of course, you need to validate your model to see if it is significant. Sometimes you can't come up with a correlation. So you need to look for significant differences only. So we screened a different type of exosomes. We have multiple cell lines, different exosomes. We incubated them with, so you can have a different, so rather than having one exosomal type with all the cells and so on, you can think, if I would like to do this in a standard way, I would do 4 times 3 times 3 times 3. So that's the number of conditions. If you do the DOE design, you set up certain levels of what you want, and it gives you a matrix that doesn't necessarily require to do you to do all the combination. You have say a number of 20 or 30 conditions that will make sure that you're covering all the low and high range of the study, and it gives you an equation at the end. When we started culturing these exosomes, we used to use T75 flask, and everyone was complaining that Farid was occupying the tissue culture incubator. So we need to find ways of using less space. So we worked with collaborators from Cardiff, Alid Clayton, and Farid spent time in his lab. We adapted a new method of culturing to do these bioreactor flasks. So what you can get from 10 flasks maybe can be got in one flask. So you reduce the space and you reduce the volume you require. You get rid of all these large vesicles that are above 100 nanometer in size, because exosomes will be below 150, 100 nanometers. So I get rid of all the large particles, and then I get the small particles by centrifugation over sucrose cushion, because that matches the density of exosomes, and you end up having a tiny pellet that actually you can use for subsequent applications. So Stephen has done a lot of that in the lab, and he's experiencing it now. We then control or check the size. So the size has to be in a range of 100 nanometer in size. We look at their positive charge or negative charge. We measure a concentration of how many particles you have in a ml, because that's important for dosing. So this is different from liposomes. With liposomes, people don't use particle, they use just millimolar. But here we always dose with particle number. To ensure that sometimes the cell condition require you to put different amounts of protein, whether you have PSA or fetal bovine serum, you end up having different amounts of protein in the formulations. If you rely on the protein quantity to dose, that can be misleading. So what you can do, if you want to do the protein for dosing, you need to ensure there is a high quality formulation that is rich in exosomes, less in the protein. So there is something we call exosome to protein ratio. You count the particle per microgram protein, and anything above 3 times 10 to the 10, that's considered acceptable quality, and you can rely on the protein for dosing. I told you about imaging. So what we really need to do is find a way to functionalize these exosomes with a dye that allows either in vitro tracking or in vivo tracking, and see where they go in the body or in the cells. And Litzo developed a protocol where we use the amine service of the amine of the exosomes, because there are many of them. You react it with a DBCO linker that then will allow the acid amine reaction. So it's kind of a quick reaction that then introduce an alkyne group, that then you have a dye with azide group, and you have a click reaction, and you get your labeled polymer. You can change this dye to something that's suitable for confocal microscopy, flow cytometry, near-infrared imager, whatever you prefer, and you purify the free dye. And why we need to purify the free dye? Because I don't want to have any artifact. A lot of publications give false data, because sometimes what you see is the behavior of the free dye and not the exosomes. And it's a very important point to consider, to ensure you've removed your free dye, to ensure you always have your free dye control to compare, so you don't get misleading data. I talked about the DOE, so we basically put the metrics in. We get some data that allow you to measure the observed number of particles taken up by the cells. And this is what the model predicted. So we can see there is a good correlation between the observed and the predicted uptake numbers. So I get an equation that you can see from the R square value that this is a reproducible model to use. So next time I want to do it, I would just know using those equations how much particles I need to get this number of uptake. So I told you we wanted to find what exosome type we would like to test. So I have different type of exosomes, all incubated with pancreatic cancer cells. And what you see here is a color coding. And what does that mean? The red color means you have more particles taken up compared to the blue. So this means I have 7 times to the 8 particles taken up in the cells, while this is means 1 particles times to the 10. So if I incubate a dose of 15 times to the 9 for say 3 hours, that's what I'm gonna get. If I incubate 25 times to the 9 for 24 hours, that's what I'm going to get. And what I would like to tell you here is you can see if I incubate using the same dose, the same time into the cells, I will get higher uptake in pancreatic exosomes in pancreatic cells compared to other type of exosomes in pancreatic cancer. So we actually verified that there is higher affinity of panc exosome to panc tumor. So it is at the moment favoring I should use pancreatic exosomes for the treatment. We incubate these labeled exosomes with cells. We take pictures of the cells, and you can see that the green signal indicate uptake inside the cell. On the x-axis, you have the period of incubation, and what you can see here, the green bars shows higher uptake, and these belong to BANK1 exosomes in BANK1 cells. So one, you see the dose-dependent uptake. So there's continued uptake of these exosomes. There is only saturation after 24 hours. And in general, the uptake level is higher than melanoma exosomes and non-cancer cell exosomes. So there is some sort of likeness between the cancer cells and their daughter exosomes. We also look if there is a saturation. So can I add a lot of exosomes to the cells? Will they continue taking them up? Will there be any saturation? And you can see that there's actually no saturation. The more you add, the more the cell is likely to take them up. While if you have foreign exosomes, they will plateau, the cell will take them, and then they will say enough. And that we think is because you have different kinetics of uptake. So if you have the mother-daughter relationship, there are different ways of internalization that you don't get saturation. You have multiple pathways. But if you have the foreign one, there's one way of entry, and that is controlled, and you get saturation, or you can get just a linear relationship. So further studies are required here to understand the mechanism of internalization of exosomes and why some exosomes behave differently compared to the others. If possible, I would just like to have 5 minutes break. Is that okay? Just have a glass of water or something. Yeah.
Yes.
Yeah, just a few minutes. Yeah, thank you very much.
While waiting for Prof. Kulot, for participant who has already have question in mind, please just chat in the chat column.
Hello.
Yes, please. Welcome
Back.
again.
Thank you very much.
Yes.
Okay, so uptake. So we look at the uptake in these animals. We took the mice, we implant the tumors on their flank. So these mice has to be immunocompromised because you are giving them human cells. So human cells cannot grow in mice, so you need to suppress their immune system. So these mice don't have a good immune system. The particles are labeled with CY7 dye, which is a near-infrared dye, and we look at the biodistribution. So this is a whole image of a mouse from the top, and you can see this, the tumors are on the back of the tumor, and the tumors are taken up. This is the free dye. So the tumors are brighter than the rest of the body because the dye will go everywhere. Now, this is what we expect. If you put them in exosomes, they have the more localized uptake that I described to you. And when the mice are done at 24 hours, we open the mice up, we take the organs, and you can excise the tumors and you look at the signals. What you see here is that tumors incubated or treated with the exosomes are brighter than the counter group of the dye alone. So we can tell that these exosomes are taken up more significantly better than the dye alone, and this is the background reading. You also can see there's uptake in the liver, the kidney, the spleen, and other organs. So what I would like to highlight with targeting, you don't stop the dye, the particles going anywhere, but you have more ratio of the tumor than before. For example, it's very hard to bypass the liver. If someone can bypass the liver, this is a big achievement. But you can see there is uptake in the tumor, and what happens if I, oops. Okay, so what happens if we do the same experiment, but implant tumors that are not pancreatic cancer? These are melanoma tumors. And what you see is the exosomes are like the dye. They don't particularly recognize the tumor any better. So what we see about the homing of the exosomes, the tumor is actually real. And there is some sort of interaction signaling that allow these accumulations to happen. We know what exosomes we would like to give. Now we go and load them with sRNA. sRNA are approximately 13,000 Dalton. We have a fluorescent tag on them. We do electroporation that makes little pores in the exosomes so that sRNA is internalized. And we look at how much, we quantify how much exosomes nucleic acid get into the exosome. We know that there are approximately 30 to 80 copies of sRNA per one exosomes, which is quite a good yield. Now, what we expect is that exosomes will be taken up by cells. So these are flow cytometry plots showing the cells that are not treated with the exosomes are dark, but the cells exosomes treated with the exosomes are bright, means they took up the signal, whether they are with or without sRNA, they are taken up. Now, if you look at the label coming from sRNA, you can see the shift in the green group, which is exosomes that have been introduced to the exosomes, which is sRNA introduced to the exosomes by fluorescence labeling. So we successfully helped the sRNA, which is highly negative, large in size, to enter inside the exosomes by this method. Now, you can see here, this is the exosome uptake in green. This is the sRNA uptake in yellow. You can see there is some co-localization, which means they are still together in some places. But in others, you can see also that the sRNA actually escaped these extracellular vesicles. So we have a proof that sRNA can be efficiently delivered. Is it active? We look at PAC4 protein expression. So what I expect is the cells will produce PAC4. If I knock it down with a positive control like lipofectamine, there will be reduction. If I use my alternative vesicles, I also should have reduction comparable to that of lipofectamine. What you see here, even with 12 nanomolar siRNA concentration, you have a knockdown that is comparable to 30 nanomolar using the lipofectamine positive control. You may ask me, lipofectamine works, why don't we use it for in vivo studies? Because lipofectamine is not effective for in vivo study, and it's also toxic, so we need to find a more suitable carrier. So these are just quantification data to show you have actually the exosomes actually performed better than lipofectamine at the same concentration. What happens if I knock down PAC4? I expect the cell migration to be stopped. So what you do, how do you test if your siRNA is functional? Your cancer cells are seeded on a plate. You create a wound inside the plate. And with time, these cells will migrate and fill the wound again. And this is what happens in our body. This is how the cell migrates. So if I treat them with siRNA, SI-PAC4 siRNA with exosomes, you can see that migration into the wound is reduced, which means I'm able to, my siRNA is functional, is doing something. And this is your control where you use a siRNA that is not coded for PAC4, it's just a negative one to show that this is not a toxic effect of exosomes. And you can see the cells are migrated. So the effect is actually specific for the PAC4 silencing. And this is just measuring the number of cells in the wound area, and you can see there is less migration in case of our exosomes PAC4. Okay, so does this translate to in vivo studies? We take the same mice, we implant them with a tumor, and we look at the tumor growth. So you have a caliber, you measure the tumor size, and this is the tumor volume over time. And you can see there is increase in the tumor volume if you don't treat them or treat them with the negative exosomes. But if you treat them with the PAC4 exosomes, you have a more controlled growth of these animals, and that leads to improved survival of these mice. The mice are able to live longer compared to untreated mice. One could argue this is just an effect of exosomes. It's nothing to do with PAC4. So you need to prove to me that the PAC4 protein is actually reduced. So we use immunohistochemistry. These are the sections of the tumor. And you can see any blue stain means you have viable cells. Any pinkish stain, you have dead cells. So we exclude these necrotic areas. And then you look at the viable areas and quantify the brown signal. The brown signal is how much PAC4 you have. And you can see if you treat them with the PAC4, you have reduced expression of the PAC4. So we could actually assume that the silencing of PAC4 has been the reason for reduced tumor growth. You monitor body weight, a sign of is the treatment tolerated. So you can see the mice without treatment, they lose a lot of weight and we have to kill them. The mice with the treatment, they are more coping well with the tumor. We take the organs, we measure their weight to ensure there is no toxicity on the organs, and we don't see any changes in organ weight, and no change in liver enzymes as well. So we use a positive control, which is polyethyleneamine, another polycation, which is used also for animal studies. And we saw PI actually works. It delays tumor growth, but it has liver toxicity. So you can see the liver weight is reduced, and you can see there are elevated liver enzymes level in these treatments. So what we could offer is a safer treatment, maybe not more potent, but a safer treatment. So I would like to summarize by saying we functionalize these exosomes. We apply design of experiment approach to pick our best candidates. We perform in vitro study to show that they are functional, and also in vivo efficacy study to show that we are able to delay tumor growth. Sometimes you would have results in vitro, but when you do it in vivo, it doesn't work for multiple reasons. So it's very important that you do in vitro to in vivo correlation. So I will talk to you about, I know you want to have half an hour of discussion, so I could continue talking for another 10 minutes, or I could stop and take questions. What would you prefer?
Yes, please, for another 10 minutes, if you please.
Yeah, of course.
Yeah, okay, thank you.
Yeah, so I'm happy to stay beyond, I think I can stay beyond 11, but yeah. Okay, so we use exosomes to treat pancreatic cancer. Can I use them to diagnose pancreatic cancer? So how do people use exosomes as biomarkers? Every cell in our body can produce exosomes. Exosomes are present in fruits, in milk, in everything. So what are they? They are a byproduct of the cell. When the cell undergo biogenesis, they start producing extracellular vesicles. They shed these extracellular vesicles out, and they are responsible for cell-to-cell communication or paracrine effect. Now, I would imagine someone with pancreatic cancer would have exosomes circulating in their body. These exosomes should have biomarkers. It's just we don't know what these biomarkers are. If I'm able to find a way to detect more sensitively and early those exosomes, and if I'm able to fish for specific markers, then I can detect the disease early. And if I detect it early, I would have better success in therapy. So that's where we want to explore them now as a disease marker. So there are various types of markers you could look at. You could look at proteins, you could look at RNA, DNA, lipids, really a range. For point of care, the easier one is to look for cell membrane markers. I'm sure there will be ways to also look for intracellular marker, but it will have to have a clever way if you want to adapt it into a point of care device where you are in a GP clinic, you take serum sample and you put on the chip like the pregnancy test and you see a color change. So what Litso wanted to do is actually take cell liquid biopsy. We don't want to be invasive. We want to take blood sample and look at these exosomes and try to find some of the markers. We were first interested in the GPC1 marker, but actually we couldn't get good expression of this on pancreatic cancer, so we left it and we were looking for other types of markers. There are publications looking at how some of the proteins were used, or circulating DNA, or panel markers, multiple markers. I think the way to go is look for multiple markers, not just one marker. But here we wanted to have a proof of concept that I can develop a colorimetric method to do that. So ideally, you want to have a system that does the separation and the detection. We don't have this yet. We are only looking at the detection, but as a continuation, we are now trying to develop a 3D printed device where you can do the separation. Because if you remove those large vesicles, you are left with exosomes, your desensitivity will be better. Rather than I label a mix of small, large vesicles, I label only my exosomes. So certainly I will have better sensitivity. But it is important that you know that you actually need a separation as well as a way of detecting them. There are various methods of detecting. Some of them rely on the color, some of them rely on electrochemical changes, mechanical, and so on. So what, I mean, I will not go in details in this, but what ideally we want is something that is portable, high throughput. Electrochemical detection appears to be one of the very good system to do that, and this is what we're exploring now, but the work I'll show you is with the optical color. So how do we do that? We would like to develop a biosensing system that relies on aptamer, and the aptamer is like an antibody, substitute of antibody, a small targeting ligand that will recognize a molecule on the exosomes, and we want to generate a color. So I'll tell you how we've done that. So because we are developing a new way of detection, we need first to work with markers that we know are released in the exosomes. So HER2 is a receptor that is known to be released in exosomes released from pancreatic cancer that are HER2 positive. So what I would first do is work with aptamer for HER2, optimize my detection because I don't have any doubt that exosomes do not have HER2. And then once this is developed, I can switch HER2 to another aptamer for my unknown marker, because I would like to see if that new marker could be used to detect pancreatic cancer. So there is lots of evidence that HER2 is expressed on exosomes. There is also a paper to show that there is a correlation between level of expressions on tissues correlate well with level of expression on the exosomes, multiple data to prove that. So what we are interested in, however, is another integrin biomarker called integrin alpha V beta 6, because integrin receptor is highly expressed on triple negative breast cancer, it's highly expressed on pancreatic cancer, and it's very low expression on healthy tissues. So we validate with the HER2 aptamer, and then we optimize the assay, and then I switch to alpha V beta 6 aptamer and find if they are expressed on the pancreatic cancer or not. These are just examples to show alpha V beta 6 actually was found in exosomes from pancreatic, from prostate cancer. So there is an evidence that they can be released in the exosomes, but not on pancreatic cancer. We didn't have any proof that they could be present on pancreatic cancer. So this is the assay. It looks easy, but actually let's spend a lot of time trying to optimize it. And how does it work? You use these beads. These beads are functionalized with aldehyde. They will capture the exosomes. And that's why pre-separation is important, because you don't want all vesicles to bind, you just want exosomes to bind. You then have the aptamer that recognizes the receptor. This could be service marker receptor, HER2, alpha V beta 6, whatever you want. You get an aptamer designed for that receptor. The aptamer will have a streptavidin-avidin reaction with an antibody, secondary antibody. And then in the presence of hydrogen peroxide, you would get a color. Now, this color could be intensified if you allow polymerization of dopamine to polydopamine and form a more intense color separate from the substrate for hydrogen peroxide. So when you get this intense color, and because of the high surface area, you are likely to get a detectable color that you can see by eye. So the higher expression level of this receptor, the higher the intensity of the color is, and you can see it by eye. And this is just to show you the molecular polymerization of how you would form PDA aggregates on the surface of exosomes. So first, we get the exosomes from cell culture because we want to use service markers. So these are characterization showing the exosome size, the presence of service marker that confirm you have exosomes. So something like CD63, CD9, CD81. These are all tetraspanins to confirm that what you have is exosomes, not other type of extracellular vesicles. They are small in size, about 100 nanometer in size. So we start with an aptamer for a marker we know is definitely there, CD63, and we optimize the reaction condition to see when do you start getting the color. So you can see here, you get your limit of detection is approximately 2 times 10 to the 3 of the particles. So you get about 1,000 particles per ml. Now, if you're looking at early detection, this is not good enough. You need to be able to detect smaller particles because you want to pick it up at the early progression of the disease. Now, again, validation, very important for us. And we looked at CD63 expression from our standard curve on different types of exosomes. And because we have another method relying on flow cytometry, I can also measure the level of expression on these exosomes. And we found there is a correlation in terms of trend. So we believe our standard curves. We've used liposomes that are not meant to react with this assay because they don't have CD63 to avoid any interference from the hydrophobic lipids. And again, I can only see the increase in the PANC1 exosome. So it's a specific to exosome reaction. We optimized step by step, for example, here, switching from a dot plot assay, the normal one without the polydopamine, and then we switched from an antibody detection to an aptamer detection. So step-by-step optimization till we get this reaction that relies on the aptamer and relies on polydopamine formation. And here you can see how the sensitivity increased as you go from the conventional to enhanced detection, switching from an aptamer to an antibody. And what I would like you to point here is just the x-axis range, how the sensitivity increases with optimization of the assay. We look at HER2 expression on cells, on exosomes from different types of cells. And we know, for example, this cell line is positive for HER2, and we expect the exosomes to be positive. So we can also confirm that there is HER2 expression which agrees with our knowledge of expression in the parent cell line. And this increase is dose dependent if you increase the concentration of exosomes. Now, this is the surprising or the new knowledge for us is, can we detect alpha V beta 6 on exosomes? And yes, we can. We can detect them in exosomes from cells that contain alpha V beta 6. And if you increase that concentration, it is dose dependent. Now we move on to patients. We take patient samples that contain HER2 exosomes. And when we screen those patients, so these are control patients with no cancer, and these are breast cancer patients, you can see there is higher level of HER2 on their exosomes compared to the control. So we can detect HER2 positive population by looking at their exosomes, just simply by taking the blood, take the serum, and isolate. Now, this is not really a point of care as such, because we still need to do the different separation by centrifugation. So this is where we're trying now to improve by doing this all in a lab on chip, where we don't have to do the centrifugation steps. And if you look at the alpha V beta 6 concentration here on exosomes, you can see that there is a specificity to only the cells that are positive for this receptor, and those are the patients. So the patients with pancreatic cancer has more color in their exosomes compared to control or compared to patients with breast cancer. You can see that even breast cancer ones have slight expression of this, but not to the same level as pancreatic cancer. So we think alpha V beta 6 is a potential marker to look into for diagnosis of pancreatic cancer. Okay, so finally, I would like to thank my team for supporting me throughout these years, particularly thank Lizzo and Farid, who actually drove this work that I have shown you today, particularly Farid, who was the first one to start working exosomes in my lab, and the other team members that contributed to the generation of data, either as being master students like Ray, who's now a PhD student, but her master project was on the exosome first, and all our collaborators who also helped us optimize our assays and maximize the knowledge we gained in our lab. So that's for me. Apologies for being too long, but I was asked to speak for this amount of time. So now I'm happy to take any questions from you.
Okay, thank you, Prof. Khaled, for the very interesting talk, and also very impressive that yes, it's remind me for some times ago that I attended in European Science Controlled Drug Delivery that time, if you remember, on 2016 that we met ever before. So yeah, so it's very glad to seeing you here again, and also hearing your another research. So we have already some question here in chat room.
Mm-hmm.
Let me read you.
I can read them if you like. So they are.
It's a first from Prof. Hakim Bangun. It's about exosome.
Okay, so for those who want, okay.
The exosome.
Okay, yeah. As a drug carrier to pancreatic cancer, is the exosome act as passive or active targeting? I think there are two ways. One is they have an effect themselves on affecting or modulating the tumor microenvironment, because we believe that they have an effect on making the environment more fluid and stopping the resistance to flow. So how to do that? Maybe there is an effect on other cells, like stellate cells, for example, in the environment. So to know whether the uptake is active or passive, I mean, if you consider active as you have a targeting ligand, we don't have a targeting ligand, but there might be some endogenous molecules that are promoting active targeting. We don't know. So passive is likely to refer to when you don't really rely on any receptor interactions, but I believe there might be some receptor interactions. So it could be mixed. That's my my answer to that. There is second question.
Yes.
I read some information that exosomes have been shown to regulate both development and progression of pancreatic cancer. So if we use exosomes as a carrier, is not exosome to develop pancreatic cancer. So very good point. So at the moment, we are looking at the use of mesenchymal stem cells to generate exosomes for delivery. And that's because we believe pancreatic cancer exosomes are never likely to be translated. How do we know if there is any effect on promoting cancer? So you're right. Now, so the first thing is we're replacing those cancerous exosomes with a more regenerative one, such as MSCs. But even the MSCs, there has been report that they can induce proliferation of cancer cells. So we need to think when we're using these carriers that we would like to add some agents that counteract this proliferation, or retargeting them to cells other than pancreatic cancer, like macrophages, stellate cells, other immune cells. So I would like to hear if Prof. Hakim has more questions, or if that's clear.
Prof. Hakim, you can unmute if you already satisfied with the answers, or want to explanation further, or how is it? Prof. Hakim Bangun, can you maybe from the from the committee can unmute Prof. Hakim Bangun to talk, please? Mr. Sony, can you help to unmute Mr. Hakim Bangun? While waiting for Prof. Wood, can standing for this exosome question. How about
I think he's unmuted now.
Oh, okay, so yeah, please, Prof. Hakim Bangun.
Okay, how are you, Professor?
I'm very well. I'm very well. Happy to be with you.
Okay, I was the advisor of Stephen during his undergraduate research.
Ah, okay. He's yeah. I won't promote him so much.
Yeah. So I am glad Stephen take a master degree under your supervision.
Thank you very
And
much. We're delighted.
hopefully, he can enter the doctoral program next year.
We hope so. We hope so.
Hope so.
Yeah. Okay. Thank you for your explanation. I think it's clear. Yeah. Thank you very much. Yeah.
Thank you very much. I think there are lots of unknowns. I mean, we have to admit, I'm not promoting them as carriers, but this is the knowledge we have so far. So there are challenges to overcome, and we have to be real on what the problems are. I agree with you. Okay, so I move on to the question from Ali Afan. Thank you very much. So can delivery using liposomes other than cancer, for example, we only deliver drugs to pancreas without going to other tissues, and whether the drug release using liposomes can be modified? I believe he's asking whether we can be very selective in targeting them to the pancreas. At the moment, even with liposomes, with pegylated liposomes, you cannot avoid uptake in the reticular endothelial systems like liposomes, spleen, and the lung. And that's simply because the liver and the spleen are meant to be reticular. They're meant to trap any types of particles. Now, there are ways, for example, giving some drugs that deplete the macrophages from the liver, but just by delivering them to the pancreas, this can only be achieved if you do local administration, which is, possible. Maybe we can do intraperitoneal administration to maximize the delivery to the pancreas. But we need to remember that the limitation is not just getting them to the cells, it's actually allowing them to penetrate into the pancreatic, into the tumor masses. So we need to modulate that fibrous nature. So two ways to tackle the tumor. Okay, so any more questions? Maybe someone would like to ask these other ones on the chat.
Yes, Prof. Kulot, continuing your that you mentioned about the pancreatic environment, about this fibrotic, that that its pancreatic is a very rich, very fibrotic, right? And how is this exosome that we can see that you have an uptick there, and I'm just wondering how is the exosome can counteract this fibrotic environment in pancreatic cancer.
So if we look at the experiment where I compared uptake of exosomes in pancreatic cancer versus melanoma tumors. Melanoma tumors are highly vascular. So when you actually excise the tumor, you can see it's very squashy, it's full of blood vessels. So we were very surprised to see there is more retention, more permeation in exosomes in pancreatic cancer. So although we have not done it, I think what we can do in the future is try and stain the actin filaments, stain the collagen, see if there is any loosening of the matrix, because we don't understand why there is better penetration. We also need to stain where they go in the tumor mass. What I've shown is a whole tumor, but maybe have some confocal sections. So it can be a project on its own. Now, because I'm interested in delivery, I would like maybe to do this with someone who's interested in trafficking, so we can stay in our area. Lots of exciting things. It's just whether we want to focus on them or not. That's the question.
Yes, it's very interesting, and we also very interesting that if we wonder if we have also make a collaboration on this thing, this nanomedicine, and also the penetrations.
Sure, of course.
Sure. We hope that we can discuss further, and maybe not this time, but we can. I hope that we can arrange another time to discuss again. Yeah,
it will be my pleasure. Yes.
I think the time is we close to the end, and the question for still there's one. Do you have one for one question more?
Yeah, I see.
It's from Debbie Fajar. It's asking about, are there any in vivo studies of the exosome performed in advanced model? How was the outcomes?
I don't know what she means by advanced. But for example, I can tell you we are now looking at liver diseases, so other type of diseases. But maybe Fajr, you can explain what you mean by an advanced model. Maybe KBC.
The KBC model, yes.
What do you mean by KBC? Sorry.
Debbie, can you, Sonny?
Like orthotopic model?
I think so. Yeah, Debbie, hello, how are you?
Hi, how are you? This is Dwi. It's very nice to see you again virtually.
Yeah.
It's been almost 3 years, I guess.
Okay, nice.
Yeah, and hello, Professor Ajalmal.
Hello, Fajr.
Hi.
So what do you mean by KBC? Apologies for my ignorance.
If I'm not mistaken, it's a genetically engineered model in which the pancreatic cancer is more advanced and can progress metastasis. If I'm not
like
mistaken.
virally induced, for example. Virally induced.
No, I guess
so.
not.
A metastatic model or an orthotopic model?
Metastatic.
Okay.
Yeah.
We have not. No, we have not tested that because mostly with the type of tumor models, it's very highly regulated here, and I don't have this particular model, but it's something we could, if someone has the model, we could provide the exosomes, but we haven't done that ourselves.
All right. Yeah. But can I have one more follow-up question, please?
Yeah.
Yeah.
No problem.
What do you think about this exosome in fighting? Let's say, can this suppress metastasis, or in some model, in some other kind of nanocarriers or nanomedicine, or maybe other? If let's say if we only use anti-cancer agent, the anti-cancer can provoke the cancer to metastasis. Please correct me if I'm wrong, but what do you think the benefit of exosomes in this matter? Thank you.
Okay, so exosomes are carriers. So you need advances on the delivery, but you need advances on the treatments. And nowadays there are advances in addition to chemotherapy. So immune modulation is very popular now because we believe we need to also modulate our immune system. Now, advances in both delivery and targets and treatments, I think altogether can work in better treatment. So if I have good delivery system, but bad target, the effect is not good. If I can have good target, good delivery system, that's what can be achieved. So we need to work together with people who develop new targets. We're exploring them at the moment for gene editing. And this is a project that we're doing with Farid now for gene editing for cancer applications. How can we, for example, modulate immune checkpoint inhibitors to treat cancer? So I think it's all answers has to be evidence. I can't tell you one is better than the other. It has to be done in comparative study where it's all a standalone. So we will tell you maybe in a few years' time, Fritz will have some answers for us. Yeah.
Okay, Devi Fajar. Okay, thank you, Prof. Kulot, for a nice talk and also the great answers that explains all of us. And I think it's the last question. And yeah, we hope that we can meet in another discussion further. So yeah, to conclude that yeah, with the nanomedicine, especially with this exosome, that we can modify the drug or the therapeutic to the specified targeted organ, and so we have yeah, some benefit of it. Okay, so thank you, Prof. Kulot, for the great talk. And the time I will give back to the Mr. Emil as the master of ceremony. Yes, thank you.
Thank you very much. Thank you.
Yes.
Okay. Thank you, Mrs. Dwi. Great talk from Professor Kulot. Thank you, Prof.
Thank you. My pleasure.
Now I would like to invite the Dean of Faculty of Pharmacy, Universitas Sumatera Utara, to give certificate to our speaker, Professor Kulot. Please welcome Dr. Khairunisa and Professor Kulot.
Thank you.
So wait a minute, we will share the certificate.
Mhm. I think I see it. Thank you very much.
Okay.
Thank you.
Okay,
Thank you.
Thank you very much, Prof.
You will send me this certificate?
Yes, of course.
Sure.
We will send the certificate through email. Thank you very much. Nice
Thank
to
you
meet
very much.
Prof.
Thank you. My pleasure meeting all of you, and I hope to meet you in person one day in Indonesia.
Yeah, thank you very much.
Bye-bye. Take
Okay.
care. Bye-bye.
Yes, thank
Okay,
you.
thank you,
Stay
Prof.
safe
Thank you.
and healthy, everybody.
Thank you very much. Thank
Thank
you.
you very
Bye-bye.
much.
Bye.
Bye.
Okay, everyone, this is the end of our event. I hope this event increase our knowledge about exosome in pancreatic cancer. Thank you for joining us today and have a great rest of your day. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you, Mr. Emil.
Thank you.
This is great. Thank you very much.
I hope everybody can.
Thank you. Tadi nggak
Halo
boleh.
Debbie, how
Kalau
are you
bisa-
Debbie? Oh my God. You.
Ya, boleh kan tadi nggak bisa ngomong ya?
nggak bisa ngomong.
Iya, unmute
Iya.
nggak bisa otomatis. Aduh,
Iya,
saya.
harusnya.
Halo,
Ya,
ini
kira-kira
perkenalkan,
seperti
ini
itu.
Mr. Debbie Fajar, my colleagues also, we have
Siapa?
done together.
Salam kenal,
Fajar.
Mr.
So we
Fajar.
so we are three.